I have dedicated a lot of videos to the application of the Statistical Tools plugin, as well as the XY plot plugins in my playlist number 5. There are more than 29 videos in there that you can look at. But there are a few functions in the Statistical Tools plugin that we haven't looked at, and so I'm going to do a quick review of them in this particular video. We're going to start with the Bessel function. Bessel functions are functions that solve a particular type of differential equations. You can find recent information in the Wikipedia pages related to them, but I just want to mention that when you do statistical tools, and we open functions here, and the statistical tools, you get for all functions Bessel. We're going to use specifically Bessel J and Bessel Y. And these are the so-called Bessel function of the first kind and Bessel function of the second kind. And so Bessel J alpha x is what typically is in mathematical text refers to J's of alpha of x. And this would be Y's of alpha of x. To calculate that, simply type the word Bessel J with the particular parameter alpha and the value of x that you're trying to find. Here are some examples of Bessel J and Bessel Y. You cannot simply type Bessel in here and get this plotted. If you want to plot those functions, you have to go this way. First, create a range of values that has a very fine grid. And so what I created is XX. I say XX double dot range 0, 20, 0.1. So we're going to go 0, 0.1, 0.2 to 20. So there's a lot of numbers in there. And then use the vectorization of evaluating the Bessel function. I evaluated for alpha equals 0, alpha equal 1, and alpha equal 2, and created matrices augmenting the value of x with the corresponding value of y for the 3 cases. Then I created a collection of those matrices using a system, and that's what I use for my entry point in this XY plot, and it shows those oscillating functions that represents the Bessel function of the first kind for alpha equals 0, 1, and 2. Then down here I do the same thing but for the Bessel Y function, basically repeating these calculations but for Bessel Y, and so the plot shows this collection of functions for the Bessel function of the second kind. Then we have the beta function and the beta regularized function. You can find information about that in Wikipedia again. Beta function requires x and y parameters. Beta regularized requires a z parameter for parameters x and y. So if I take alpha equal 2 and beta equal 3, which would be the first and second parameters, the calculation for the beta function is simply this value. The beta regularized, I can give values of an independent variable for the first argument, and I can produce a plot of that beta regularized function for the parameters alpha equal 2 and 3. Again, I'm just showing you the application and not giving you any information about the operation of the definition of those functions. Dirac and heavyside function. Dirac function is used to represent a pulse in the time domain. For example, if the pulse is located at x equals 0 or time equals 0, anything below 0, like -1, the value of the signal of the function is equal to 0, and past 0 is also equal to 0. But at 0 itself, where the pulse occurs, that pulse has an infinite value. If you have 2 arguments, you can switch the origin. So I'm switching the origin to 1 at that point. Then when x equal to 1 and the rect function is located at 1, my pulse goes to infinity. But everywhere else about that point 1, it goes to 0. If I try to type or to plot the rect function, I get nothing. I get just like a horizontal line, because at the point where the function goes to infinity, it's a single point, and it typically is represented when you draw that by hand with an arrow at a particular point indicating that that value is going to infinity. The heaviside function is also called the step function, and what happens is that at the point where the step occurs, the function goes from 0 to 1, and so exactly in that middle point will be 0.5. If it is switched to another point, then it would be at that point where the function goes to 0.5. By the way, in terms of mathematical notation, the Dirac delta function, and consult theory here, is represented by delta of x. But if it is shifted, it's represented by delta of x minus a. Whereas the heaviside function is represented by h of x, and if it is shifted, it's represented by x minus a. A is the point where it shifts. There is also a heaviside discrete function, in which case, at the point at which the step occurs, it just goes directly to 1 instead of being 0.5. These issues are used in control theory. The heaviside step function is easy to visualize, and the Dirac delta function is represented by a step at that particular point. The error function is a function that's related to the normal distribution. There's the standard error function written as ERF. There's the inverse, when P is a probability, or sort of a number between 0 and 1. The error function can be shifted at point A. There's something called the complementary error function, which is 1 minus the error function. And that complementary error function can be shifted about x equal a. Again, you can find information about the error function in Wikipedia, the same as Dirac and heaviside. Gamma regularized functions. There is something called the incomplete gamma function, and it's not presented in the collection of functions in here, but you can find all kind of information about the gamma function in this link. And so if you have that incomplete gamma function and divide by gamma of a, it gives you this so-called gamma regularized function P. And then there's the gamma regularized function Q, which is the actual gamma operating the operating complete gamma function is the uppercase gamma. This is the operating complete, and then there's the lower incomplete, which is the lowercase gamma. You may want to find information about that in here. I don't know whether they're included in the statistical tools, probably because they are using some probability definitions. I just wanted to cover up all the functions presented in there. Graphs of the gamma regularized functions are presented in here. Gamma regularized P and gamma regularized Q. Then a couple of statistical functions that escape my playlist number 5. If you're given a couple of vectors representing data x, y in the plane, I represent them here as row vectors. So in order to produce a matrix, I put the transpose in here. And so it shows some increasing tendency, and it may be fitted through a straight line. And so statistical tools has a function called slope that will give you the slope of the line, represent the best line, the best fitting line to those points. And then there's also a function called intercept. And remember, the straight line is simply slope times x plus b. And so in here, I'm showing the original data and the fitted data. Then there's something called the weighted mean. In the past, we used the function mean in the collection of videos presented in my playlist number 5. And if you want to calculate the mean of a vector, simply use the function mean. This is a function from the statistical tools package. But suppose that these mean values are associated with certain frequency. In other words, the number 17.8 is repeated 15 times, 23.1 is repeated 17 times, 25.4 is 10 times, and so on. You can adjust the weight of these numbers in the mean by using the weighted mean. Basically, what it is the weighted mean, I'm going to call it WM, is just the sum of x sub k multiplied by its frequency. Let me try that again. Over all the n values in the vector collection. That's what it is. But there's a function already that will calculate that for you. And these are some of the functions that are available in statistical tools. I don't know if you're going to find them useful or not. But if you ever need to refer back to this video, you can look at that. You can produce screenshots of this if you need to. And I hope you find it useful sometime in your mathematical applications. And with that way, we're going to end up this video about statistical to plug in additional functions.